Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be discussing the Archimedes Principle in fluid statics. This is of course a continuation of my series of videos about fluids, fluid statics specifically. So what are some things that we need to kind of begin by recalling? Well, we have a few things here. One is that we have identified pressure. So pressure increases with depth, and basically for a fluid of constant density, meaning the fluid itself is not compressible, this increase will be linear. If the fluid is compressible, then there may be some additional effects due to this compression, but for an introductory course we don't really consider a non-compressible fluid. So obviously this equation then ends up being density of the fluid times G times H, where the depth is H and the pressure is P, and then rho is the density of the fluid. Okay, so that's item number one. Item number two would be basically the buoyant force, and the buoyant force could be looked at in two ways and both give the same answer, but the quicker way is that it is due to differences in pressure, specifically differences in pressure at the top and bottom of a fluid, due again to this equation that we just wrote up here, that the pressure is rho GH. So the bottom of the fluid is at a bigger value of H than the top is. So in some sense, those are the two main things that we need for the Archimedes Principle discussion. What is Archimedes Principle? So Archimedes Principle basically is something that you are already familiar with because I've kind of referenced it in a previous video without stating by name that this was Archimedes Principle. But you'll recall that when we discussed the buoyant force, I mentioned that the other way of figuring out what it is due to is by looking at the equilibrium conditions of the fluid and noting that if an object is placed into that fluid and displaces some amount of fluid, that the rest of the fluid must continue to apply a force back on that object as if it were the fluid that was previously present. And this is a sort of circumlocuitous way of stating Archimedes' principle. So Archimedes' principle itself states that when an object is immersed in a fluid, the buoyant force acting on the object is equal to the weight of the fluid displaced by the object. Immersed can be partially submerged or totally submerged. Basically, when you place an object into a fluid, the object displaces some amount of that fluid. That amount of that fluid has some weight. That weight is equal to the buoyant force that the rest of the fluid applies to the object. Now there's different ways of basically using this principle. Essentially, the Archimedes Principle statement could be written in an equation form. Let's write it over here actually. The force buoyant, or the buoyant force, is equal to the weight of the fluid which has been displaced. Okay, so that is sort of like the shorthand equation form of the Archimedes Principle. Now, different ways of using this, as I've said. Essentially, we expect for this buoyant force, which is equal to the fluid displaced weight, to be calculable by figuring out the volume of the fluid which has been displaced and then multiplying that by the density of the fluid. The volume of the fluid which is displaced should be equal to the volume which is submerged of this object. So in other words, if I have an object which has a total volume of, say, 1 liter, but only 90% of the object is submerged, then the displaced fluid would be 90% of 1 liter. The volume displaced would be 90% of 1 liter. And so you'd have 0.9 liters or 900 cubic centimeters is the equivalent volume. And so that's how much fluid is actually being displaced. And so then if you know what the density of the fluid is, and if you know how much gravity you have present, then you have the weight of the displaced fluid. So in some sense, this equation can be recast to say that the buoyant force is equal to the volume submerged of the object times the density of the displaced fluid times the free fall acceleration, the local gravity field strength. And notice that this right here, volume times density, this right here is the total mass of displaced fluid. So we're really using F is equal to m times g. It's just we have to figure out what our m is in this case. So this right here, I guess you could say, is also a boxable equation. Now the next question that comes of this is, so what volume of an object is actually going to be submerged? And the answer is, well, it depends upon the context of the question. For example, if I have a boat which is floating on top of water, then obviously some fraction of the boat is underwater and some fraction is not underwater. And if I have a rock which is totally sunk into the water, then the entire volume of the rock is underwater, and therefore the amount of water displaced should be the volume of the rock. But, and this is where we get some context needed, suppose I tie a heavy rock to a balloon and drop both of those into the water. Okay, suppose that the water's deep enough that for the rock to touch the bottom of whatever body of water I have, the balloon will also have to be totally underwater. The question might arise, how much of both will be underwater? And for a large balloon, the answer might be, well, part of the balloon and all of the rock. And for a small balloon or a sufficiently heavy rock, the answer could be, yes, both the balloon and the rock will go underwater. And it gets a little bit more complicated, I should add, because a balloon is flexible, and this means that if there's a different pressure applied to the balloon, then it can get larger or smaller until it sort of like pulverizes. A balloon can, if we sink the balloon for meters and meters and meters, then the volume of the balloon will actually change, and that in turn will change the total density of your system, and thus displace less water and thus have less buoyant force. But that particular question is neither here nor there. Essentially, one way of looking at this is to ask, will the object or objects ultimately float or sink? In other words, floating means that at the very least you have neutral buoyancy, or neutral buoyancy being it's neither floating nor sinking further. And essentially that's akin to the balloon and the rock will be underwater partially, and then eventually they are totally underwater and they come to a stop somewhere under the water before they hit the bottom. And they just sit there. And as long as the conditions of the water and the balloon don't change, they just sit there. They're neither floating further nor sinking further. Floating essentially means some part of the balloon should be out of the water. And sinking essentially means the balloon and rock travel together until they touch the bottom of whatever body of water they're in. Alright, so let's do a quick example. We want to know how much buoyant force is going to act on a cube of aluminum which has 2.5 centimeters to a side when it's placed in water. Now, we could get the buoyant force by essentially saying, okay, there's a depth difference of 2.5 centimeters, and so here's what the pressure is, and now we can get the cross-section area and multiply by that pressure, and that gives you a buoyant force. You'd basically use this pair of equations to get that answer. So if you wanted to plug numbers in, the pressure difference, you're in water. Water has a density of 1,000 kilograms per cubic meter. The free fall acceleration obviously is 9.8 newtons per kilogram. And then the delta H is 2.5 centimeters, so that's 0.025 meters. You basically multiply these numbers together to get the pressure difference between top and bottom. That gives you 245 pascals. So then you'd want to multiply this pressure difference times the cross-section area. Again, it's a cube, so it's 2.5 centimeters to an edge. Again, it's a cube, so you're basically looking at the cross-section area, which is this length scale squared. And so you'd have 245 pascals times the length, which again is 0.025 meters, and you're squaring that. So what you end up getting when you multiply all that together is a total buoyant force of 0.153 newtons. So we'll round that to 0.15 newtons. Now, if we want to solve it using Archimedes' principle, this is solution 2. What we do is we'd say the buoyant force is equal to the weight of the fluid displaced, which is equal to the volume times the density of the fluid, so the volume of the aluminum block, density of fluid times G. Okay, so that ends up being 0.025 meters cubed. Again, it's a cube, so you just take the length and cube it to get the volume, times density, which is 1,000 kilograms per cubic meter, times 9.8 newtons per kilogram. So if you multiply all those things together, the 0.025 cubed times the 9.8 times the 1,000, you end up getting 0.15. So your buoyant force, once again, 0.15 is 0.153125 either way, but we'll round it to two significant figures. So both of these have given us the same answer. So does it float or sink? And how much of it floats or sinks? And the answer is it floats if the buoyant force is sufficient to support the entire weight of the system. It sinks if the buoyant force is not sufficient to do that. So sinks basically means buoyant force is less than mass of object times G. Neutral basically means that the buoyant force is equal to the mass of the object times G. And float means the buoyant force is greater than the mass of the object times G. Now, in looking at these different scenarios, we might ask, what about this volume displaced thing? And the answer is, in this case, sinking, the object displaces its own volume. So object displaces its own volume of fluid. The whole object is submerged, so the volume of the object is equal to the volume of the fluid displaced. So parenthetically we can say volume object equals volume fluid displaced. Neutral, you actually get this same scenario, but as it turns out, you will also get the scenario that I'm going to write down here. The scenario that goes down here is that the object displaces its own weight. Ultimately, that also means that the object displaces its own mass. So mass of object and mass of fluid displaced will be equal to each other. Now, for this neutral condition to occur, both of these statements are true. That implies that the neutral is density of object is equal to density of displaced fluid. Put differently, the net density, the total density of the system of objects will be equal to the density of the fluid displaced, and thus if the density of the object is greater than the fluid's density, it will sink, and if it is less, then it will float. Now the floating condition has an additional thing that we might consider, which is like how much of the object is under and how much is out of the water. Put differently, what fraction of the object is submerged if the object is floating. And we can make use of the fact that the mass of the object is equal to the mass of the fluid displaced, and that the volume submerged is equal to the volume of the fluid displaced. Alright, well, mass of object must be equal to volume of object times density of object, and volume submerged, mass of fluid displaced is equal to the submerged volume times the fluid density. Set the two sides equal. Mass of object and mass of fluid displaced are equal, so that means that these volume times densities are equal, and then solve for the ratio. Thus, the ratio of the amount of the object submerged to the total volume of the object is the ratio of the object's density to the fluid density. Alright, for our closing example, ice has a density of somewhere in the neighborhood of 0.91 grams per milliliter. So we want to know how much of the iceberg do we see when we say we see just the tip of the iceberg. What does the tip mean? What part of it is not underwater? Well, the submerged volume divided by the total volume is equal to the density of the object, the ice cube in this case, divided by the density of the fluid, that is, of the salt water. So that is 0.91 grams per milliliter divided by 1.025 grams per milliliter. And you do not have to convert these units because you're setting up a ratio, so as long as they're both in the same units, the ratio is okay. So 0.91 divided by 1.025 gives us 0.8878. So that is 0.8878044878. I'm not going to write all that out. Okay, that is how much is submerged. So this is submerged. The visible part, so volume visible, or tip if you'd prefer, is equal to the object's total volume minus the object's submerged volume. So that would basically be equal to, in some sense, like V object times 1 minus V submerged over V object. Basically, I've just divided and multiplied both of these terms by V object, so a clever version of 1. So that becomes V object times 1 minus 0.8878, and so if you want, you could say like V visible by V object, dividing both sides entirely by V object, in other words, is equal to, should be like 0.12122. So 0.121 0.12195 blah blah blah. And so if we put this in two significant figures as per our above, then this ends up being about 0.11, or in other words 11% of the iceberg visible above the waterline. Alright, well that's all for this short video. Hopefully you've learned something from it, and thanks for watching.